Having seen how we can compute the area under a curve by using approximating rectangles, our next step is to make a formula approach to this. And the way we're going to build that out is to put in some general parameters. So we're going to find the area under a curve between 2 points on the x-axis, or the horizontal axis. We will call the first point A, so that's an x-coordinate. We'll call the last point B. And then we're going to use n rectangles. So n is going to be our number of subintervals, or the number of rectangles. We're going to need a little more nomenclature then to go with that, because we're not fixing the number of intervals. It'll help to have a name for all the subintervals and their start points. So A and B are the start and very last endpoints. We're going to divide the interval inside of that into evenly spaced intervals, each with width delta x. And not too surprisingly, you find the total length and you divide it by the number of intervals, which is the number of rectangles. That gives you delta x. And then for numbering or naming the subinterval start points, we're going to start at 0. So x sub 0 is the endpoint on the left, and then x1, x2, x3. And what that will give us in the end are the last 2 points, x sub n minus 1 and x sub n. Then when we imagine the rectangles, we have all these bases that are delta x, delta x, delta x. So we have all these widths that are delta x, delta x, delta x. And then we're going to have heights that go with that. So we're going to build rectangles like the ones over here. And those are going to be computed by taking the x value that we're at and going up to the graph. Well, mathematically, that's the process of taking an x value and running it through your function f, whose area you're trying to find, area underneath the graph you're trying to find. So all of these f of somethings are simply heights. And the key thing is not to get lost in the algebra here, just to think back to the concept of what are we trying to compute? The area under this curve. How are we approximating it? We're finding rectangle heights, and the heights are dictated by the function value at a point. When we're doing the left-hand endpoint, so this first rectangle here was based on the left-hand interval, which of the two boundary x's are we using? We're using the left one. So we start with x0 as our input, run that through f. On the next interval, x1 is on the left, so we use that. And notice on the last interval, we don't actually use the last x value. We use the one before it, xn minus 1. And what this boils down to, or can be more compactly written as, this formula here, using summation notation. And what this captures is the sum from I equals 1, that's this part here. The upper limit, n here, is where we're counting up to. And it's a loop. For those who have seen programming before, what we do is we take I equals 1 and we plug it into this formula. And then we get x of 1 sub 1. Oh, that's x sub 0. Hey, there's this first term, times delta x. Oh, right, there's the rest of it. And then we go to I equals 2. When we do that, we get 2 minus 1 here. Oh, that's x sub 1. So the height at x sub 1 times delta x, plus, 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 always incrementing I here. So we get x0, x1, x2, x3, x0, and so on, all the way up to the last point, n, which when we sub it in, we get n minus 1 as our x value, there it is, times delta x. So this long sum here with this indeterminate middle part here with the dot, dot, dots can be more reliably written using the summation notation. If you haven't seen this before, we're just going to go through a few more examples just to make the idea a little more concrete. Here's a simple sum using summation notation, and again, we read the I equals 1, that's the from, and then it's 2 I equals n, that's the upper limit, and this part here indicates that it's a sum, the big capital sigma for s, and this is the term or what we're going to plug x into. So this would be of x sub I. And what that means is we plug in x1, that's our starting point, and then we add, we take a sum, x sub 2, and then we add x sub 3. We always count by ones. And then we add until we reach the last value. Here that gives us a number of terms. We don't know how many, but the last two would be xn minus 1 and xn, and we would be done. So if we wanted to write out this sum from x sub 1 up to x sub n, we generalize that by saying, oh, there's a variable in there, x sub I, and we let the I value run from 1 to n in the summation notation. Let's make that more concrete by looking at sums of actual numbers. Again, the sum is from I equals 1 to 100 in this case, and what we're adding up is simply the I value. So this would literally be 1. When I is 1, we plug in 1. Then I becomes 2, so we plug in 2, and then 3, and then 4, and then all the way up to 99, and then the last term would be the 100 at the upper end here. For the second example, notice we have a different variable. That's totally fine. But again, we're going to plug in n equals 1, 2, 3, 4, 5, all the way up to 10. And then we're going to use that n value in this formula. So we'd have 1 squared plus 1 plus 2 squared plus 2 plus 3 squared plus 3 plus, and so on, up to the last two terms, 9 squared plus 9 plus 10 squared plus 10. Now you can see in this case here, this would be quite complicated to write out by hand. The summation notation gives us a much nicer, tidier form for it. Then returning to our example with the area under a graph, we have I equals 1 as our starting point, so we plug that in first. We get f of x 1 minus 1 times delta x. So we take the whole thing inside the sum here, and the one thing we might want to do to clean up early is recognize that this is x sub 0. And then on the next term, we'll plug in I equals 2, so I sub 2 minus 1 times delta x. And again, we recognize that early on as x sub 1. And then we could do a few more terms. And then the last one would be x sub n minus 1 times delta x. So this would be a way to capture a long or potentially long series of height times width calculations in a nice compact form.